Hi there, Chem Coach Powers, and here we're going to talk about some making of chemical formulas. We're going to talk about how we do percent composition and how we make empirical formulas and molecular formulas from empirical formulas. So getting into the nitty gritty of some of this cool chemistry stuff. So let's go ahead and start by going over our objectives here for the day. We're covering, by the way, we're covering just a little bit of the end of chapter 7.3, and then we're going to cover 7.4. So our first objective here is to calculate the percent composition from the formula for a compound, and then we're going to determine the empirical and molecular formulas for a compound. So by the time we're done today, you should be able to, given the formula for a compound, you can calculate percent by mass of each element in the formula, and you'll be able to use the percent compositions or the masses of elements in a compound to determine the empirical formula. And then you'll be able to use the empirical formula and the molar masses of compounds to determine the molecular formulas. All right, so let's go ahead and get started here. Now, this is really not a difficult concept, especially this first one. When we're talking about percent composition, we're talking about, can you tell the percentage of something? So for instance, if I were to ask you to do a little catalyst here, and you had a 9 out of 11 on a quiz, what would you score as a percentage? You know how to figure that out, right? You've done this over and over again through many of your quizzes and tests and things like that throughout your life. You just take 9 divided by 11, multiply by 100, you get your percent, right? Well, that's basically what percent composition is. It's just that we're going to have multiple things that we're going to determine the percentages of, okay? So instead of just 9 out of 11, we'll also figure out what the 2 out of 11 was, right? The percentage that you got wrong. And we could have multiples, 3s, 4s, 5s of those. So let's look at an example. All right, so it's percent by mass of each element in a compound. And what is this doing for us? This is letting us know what percentage we have, with regard to the substance's identity, right? What amount of this do we have in it versus that amount? All right. Is it, the percent composition is going to be the same regardless of the sample size. So if I might have a little bit of the substance versus a whole bunch of the substance, we're assuming that whatever compound we're dealing with, like let's say it's water, the percent composition of hydrogen in water is going to be the same, whether I have a little bit or a lot of it. Okay, so what's our formula? Well, we're going to take the mass of the element that's in the sample divided by the entire mass of the sample multiplied by 100. Very much like we did with our quiz, right? We take the score we got on the quiz divided by the total possible points of the quiz and multiply it by 100. And so it's the same thing here. The mass of the element in the sample divided by the mass of the sample times 100 gives you the percent of the element that's in that compound. Now, we can also do it another way, and we can look at molar relationships. In fact, the way we're going to do it for our test is going to be this way. All right, we're going to basically give you a particular formula. We're going to say, hey, figure out the percentage by mass of this element within this formula. And so you're going to use this formula here, mass of element in 1 mole of a compound divided by the molar mass of the whole compound times 100 is going to be equal to the percent of the element that you have in that compound. All right, so 3 steps basically to calculating the percent composition. First is to find the mass of the element. It's molar mass, right? We're going to pull that from the periodic table. That's the way we're going to be doing these. You're going to divide that by the total mass of the compound, the molar mass of the whole compound, multiply by 100. And then you're just going to repeat that for each element in the compound. So if you just have 2 elements, you just do it twice. If you have 3, do it 3 times. If you have 4, do it for each of those different ones. So let's look at an example. There's your formula, right? Mass of element divided by molar mass times 100 gives you the percent of the element. Excuse me. So then let's say we wanted to find the percent composition of H2O, of water. Well, what do? Well, we have to figure out what's our mass of H. Well, we look on the periodic table. We see that 1.01 grams is what we would have for the mass of H, but we have 2 of those. So we multiply that by 2. We get 2.02 grams as our mass of H. And then our water is 16.00 grams. Okay, again, we're getting these from the periodic table, looking at their total values there, the molar masses. And then we get a value of 18.02 as the total, right? We just add those together to get the total. So to figure out our percent composition of hydrogen, we have to take 2.02 divided by 18.02, and we get 11.2% hydrogen. To figure out our mass, our percent composition of oxygen, we take the mass of oxygen, which was 16.00 grams, divided by 18.02 grams, and we get 88.8% oxygen. Now, for me, with regard to percentages, I'm not worried about whether or not you have the correct number of sig figs when we do percentages. Okay, there is a way to make sure you have the correct number of sig figs and percentages. I just don't worry about it when we're doing tests and things like that. So 11.2%, 18.8%, sorry, 88.8%, that's fine. I'm usually looking when we do percentages for at least to the tenths place. Sometimes to the hundredths place would be even better, but at least to the tenths place when we do percentages, okay? So that's what we're looking for on that. All right, so here is your turn to practice this. The order of pairs is due to propyl acetate. Find its percent composition. Now they're giving you the formula of the entire compound, right? C5H10O2. So you're going to have to figure out the percent composition of the C's, the H's, and the O's, okay? So I want you to practice it. All right, so you're going to pause and practice, and then we'll come back and see how you did. And welcome back. So in order to figure this out, you had to add up all of them. So you had to figure out, well, gee, 5 carbons, 10 hydrogens, and 2 oxygens. You add all that together, you're going to get 102.13. Now you've got to take each individual, your carbons, that's 60.05. And so you take 60.05 divided by 102.13, and you get 58.80%. That's for carbon. For your hydrogen, you have 10 of those, so 1.008, or maybe you just did 1.01, times 10 equals 10.08, and then you divide that by 102.13, you get 9.87% of hydrogen. And then finally, you take your 2 oxygens, and if you had 15.999, or maybe you did 16.00, then you get this 31.998, or maybe you got 32. Take that divided by 102.13, and you get 31.33% of oxygen. So if you came up with that, you're on the right track. This is easy stuff, right? So good job. If not, make sure you talk to me, and we'll go through it some more. All right, so now we want to talk about our next concept. And this concept is a little bit more complex, okay? And the first part is actually pretty easy to understand. It's called empirical formulas. And empirical formulas are basically the lowest whole number ratio that you have of a particular formula that you have. Okay, so in other words, let's say I have H2O2. An empirical formula is going to take that and reduce it to its lowest whole number ratio. So instead of 2 and 2, it would be 1 and 1. So it would just be HO. Okay, so empirical formulas, all I'm trying to do is figure out what the formula is that would represent the lowest whole number ratio. Now, when we deal with ionic compounds, remember that ionic compounds are already expressed in their lowest whole number ratio. But empirical formulas, we are usually using these with molecular compounds. So we might have something that is pretty significant in terms of how many of these different elements we have of a particular type in a particular compound. And so we reduce them down to their lowest whole number ratio. All right. Now, we're going to calculate empirical formulas from the percent compositions or from the masses that are given to us. Now, we can determine these experimentally in the laboratory, and that's what you typically would do. You'd get an unknown compound, and you'd say, okay, well, what is in this compound? You'd figure out the percentage compositions of each of these different elements by using mass spectrometry or something like that. And then you would figure out, okay, what is the formula of this unknown compound that I've just discovered? Maybe it was something you discovered in a crime scene, and you need to figure out what it is to see if you can match it with something else. So you'd figure out its empirical formula. And then from the empirical formula, then you could determine a molecular formula. How do you do that? Well, the molecular formula is a true formula for the compound, okay? So the empirical formula takes you down to your lowest whole number ratio. But the molecular formula is going to tell you the actual number of atoms you would have in each element that are bonded together. So, for instance, if we had glucose, and glucose's empirical formula is CH2O, glucose's molecular formula has got to be a whole number multiple of that. In this case, we multiply each of those by 6, and we get C6H12O6. So what you get with a molecular formula is the true number of atoms that are present in that compound. and you have to get that from the empirical formula. We're going to show you how that calculation is done here in the next steps. So first step, if you're starting with the percent composition, you're going to just basically cross out the percentage and turn those percentages into grams. We're basically assuming a 100-gram total sample. So if I had 95% of something, I'm just going to assume, oh, well, that's 95 grams out of 100 grams. Okay, so you're assuming a 100-gram total sample, so your percentages can just turn into grams. If we give you grams, then you don't need to make any sort of assumption. Just use your grams to go to the next step. What's the next step? Step 2 is to convert each of your masses into moles. So how do we do that? Well, we got to go back to our periodic table, right? We know how to take the molar mass of something and figure out how many moles of something there is if we know the grams per mole, right? So we just go to the periodic table, pull down the molar mass, and then we multiply the molar mass by the mass that we have here in step 2. All right, step 3. Now, this one's kind of weird. It seems kind of arbitrary, but it's not. You're going to take the lowest value that you get. When you get all those different mole values, take the lowest one that you get. That is going to be the value that you divide each of your other answers by. Now, that might seem a little confusing right now. It won't be confusing once we actually do an example of this, okay? Now, remember, the reason we're doing this is because we know that all of these compounds have whole number ratios of elements in them. So if we can figure out which one is the 1 mole, okay, value, then the others have got to be multiples of 1. And so that's why we do this. We want to get down and figure out which one is equal to 1 mole of something, and then we can have values that will be whole numbers from there. And then we'll be able to determine molecular formulas from that if we want to. Remember that these are lowest whole number ratios when we do empirical formulas, and you might get some slight rounding that is going to be necessary. So, you might have 2.03, that's going to be a 2. All right, there's not 2.03 of a particular element in a compound, right? In fact, that rounding can get a little bit more, it can get bigger than that. Let's say I could have a 2.1, I could still round that to a 2, all right? And the types of problems that we're going to give you, it's not going to be too hard to figure out. If we want you to do something and not round it, it's going to be like 2.25 or something like that. And then you wouldn't round it 2.25. Step 4, you're going to use that ratio then that you get from all of these, and you're going to make those ratio numbers the actual subscripts for that formula, and then you're just going to write the formula. Okay, so right now you're probably like, what? Let's just go through it. You're going to see what it means as we do it. Okay, so it says calculate the empirical formula of a compound that has 74.2% sodium and 25.8% oxygen. So what did we say to do? We said to go ahead and just cross out those percentages, right? And turn those into grams. And so that's what we're going to do. As you see this next step, we've turned that 74.2% into 74.2 grams. All right, and then we go to the periodic table, and we see that there are 22.99 grams of sodium for every mole of sodium. So we're multiplying by the molar mass, right? Now, remember, we want the grams on bottom so they cancel out with grams on top. And so it's basically 74.2 divided by 22.99, and we get this value, 3.23. Now you're like, what in the world is 1.61? Don't worry about that yet. It's coming up right here. All right, now we take that same thing. We took our 25.8%, we crossed out the percentage, turned it into grams, right? So we've got 25.8 grams now. Now we go to the periodic table and we see that there's 16 grams of oxygen for every mole of oxygen. So it's 25.8 divided by 16, and that gives us this 1.61. So you remember in step 3, it said it was seemed confusing, but it's really not. And that's taking the lowest value. So between the 3.23 and the 1.61, which one is the lower number? Well, 1.61 is a smaller number than 3.23. So now we divide both of our answers by the lowest number. Okay, so that 1.61 we divide there and here. Now, again, why are we doing that? Remember, I said that the reason that we're doing this is so that we can get one of these values to tell us what 1 mole is, and then everything else is going to be a whole number from there. Well, look at that. That's exactly what happened here. We ended up with a 2.01 and a 1. And so what we do is we take those values and we apply those values to the formula, and we make a formula out of it. So I take the Na, and the Na is what we had here, right? And I want to put a 2 after the Na. And the O, I want to put a 1 after that. Okay, so these numbers that we come up with at the end of this, they become our subscripts. You see, that was that last step. The numbers become the subscripts. Now, remember, that's a 1, basically, right? You don't have to write the 1s when they're 1. And so you have Na2O1 or Na2O. So this is the empirical formula. I just figured out what the lowest whole number ratio of elements is in this particular compound, and that's called my empirical formula. Okay? All right. What if I don't get a whole number ratio? And this is going to happen sometimes. Like I said, if it's, for what we're giving you, you might get like a 0.25 of something, but we're not going to give you something less than that. We're not going to give you like a 0.1 and then expect you to do this. 0.25 we might expect, but we won't do any more than that. Okay, so anyway, multiply all subscripts by the whole number in order to get a whole number ratio. What? Well, let's say we had CH 1.5. Well, what would I multiply a 1.5 by in order to get it to be a whole number? I'd have to multiply it by a 2, right? So 2 times 1.5 gives me a 3. But then I have to multiply that 2 by the C1, right? That was basically a 1 there. And so that C becomes a 2. And so if you do get a situation where it's not a whole number, you just have to figure out what whole number could I multiply each of these by. Now it has to be the same whole number, multiply throughout the entire formula to get all of them to be whole numbers, okay? Once you do that, then you're gonna have the answer. Now, what are some common multiples? Like I said, we might give you one that's a 0.25, okay? In real world applications with really good scientific, really, precise values, you might be multiplying by more than that. But for right now, what we're going to give you with our examples, if you had something 0.25, you would multiply everything by a 4. If you had something that was a 0.33 or 0.67, you'd multiply everything by a 3. And of course, like we just showed you here, if you had a 0.5, you'd multiply it by a 2. Okay, so that's what you're going to do if you get something that's not a whole number ratio. So you're like, well, okay, that was a lot. How could I do this? And how am I going to remember that? Well, there's actually a little rhyme. It's kind of fun. If you do this rhyme, this is basically the steps in a rhyming format. Those 4 steps, here they are. Take your percent to mass, okay, percent composition to the total mass, right? Cross out the percentage, turn it into a mass. Percent to mass, mass to moles. Divide by smallest, multiply till whole. All right, yeah, it may not be a great rhyme, but it might help you remember, right? Percent to mass, take your mass and turn it to moles, divide by the smallest of all of your mole values, right? And then multiply until you get whole number for all of them, whole numbers for all of those. All right, so here's a good time to practice. Okay, this is a good pause and practice time. Diaminohexane is a compound used to make nylon. What is its empirical formula? If it is 62.1% carbon, 13.8% hydrogen, 24.1% nitrogen. All right, so I want you to pause and practice this and see how you do. And we're back. And this is what you did. You took the percentages and turned them to masses, right? So 62.1% became 62.1 grams. Then you took the molar masses, you divided by the molar mass for each one, mass to moles, right? 12.01 grams for carbon, 1.01 grams for hydrogen, 14.01 grams for nitrogen. Then you divided by the smallest. Which was the smallest out of all of these? Well, look here, 1.72 was smaller than 13.7 and 5.17. So you divided each of them by 1.72. Remember, this time we had 3 instead of just 2 examples. And so that gave you a chance to give this as a 1. Remember, we wanted to get one thing with the 1, and then that was going to allow us to figure out the other whole numbers for the other ones. And so we got an 8 and a 3. And if you came up with C3H8N, pat yourself on the back, you did a great job, all right? That's exactly what you were supposed to get. Good job. All right. So now let's go and see if you can determine the empirical formula. And this time we're not giving you percentages. We're giving you the grams. So basically you can just skip that first set. Remember we said percent to mass? Well, now you're already in mass. So now it's just 3 steps in your rhyme. You can skip step 1. Pause and practice, see how you do. And welcome back. Here we go. All right, so you took those masses and you took the molar masses and you figured out that there was 0.155 moles of iron and 0.233 moles of oxygen, which is a lower number. Well, 0.155 is a lower number than 0.233, so you divide them both. Now, you got this number when you did that was 1.5. Oh, that's not a whole number. It's okay, don't panic. Now you get to do step 4, which is to multiply till whole, right? So you multiply everything by 2. So you originally would have gotten FeO 1.5. Well, that's not something that can happen. We can't have 1.5 of an oxygen. And so we've got to take that to the next step, and we say Fe2O3, okay? That's your answer for that one. Okay, so now we're ready to take it to the next step, and this is going to finalize what we're doing here for today. We've got to figure out a molecular formula now from this empirical formula that we just calculated, okay? So the the molecular formula might be the same as the empirical formula, okay? For instance, in H2O, there's no, I mean, if I had something that calculated out to be exactly H2O, that might be the empirical formula because that's the lowest I can go, and it's also the molecular formula. Okay, so they can be the same thing, but they're not necessarily going to be the same thing. So you have to make sure that they are calculated, okay? So first step, you calculate the empirical formula mass. Now, that just sounds like a fancy thing, but that's what we just did, right? The empirical formula mass was just calculating and adding up the total of all of the elements. So like if we did, carbon and it had 12.01, and then you had the hydrogen, which was 1.01, right? You're just adding up whatever that total is until you get to an equal sign, right? And so there's nothing really weird about that. Empirical formula mass, just add up and figure out your formula mass of the lowest whole number ratio, okay? And then you're going to divide the molar mass that we give you. Now, this is what you're going to see. When we give you molecular formula problems, we are going to give you this value right here. Now, you may have to calculate the EFM, the empirical formula mass. You may have to do the empirical formula before you do the molecular formula, but we are going to give you the molar mass of the entire compound. We are going to give you the molar mass of the completed full compound. Okay, so molar mass of the compound is going to be given to you. You take that molar mass and you divide by the EFM, the thing you just calculated, okay? Then you multiply, this is step 3, multiply all the subscripts in your empirical formula mass by the answer from step 2. What do you mean? Well, what I mean is that this value that I come up with is going to be a whole number, okay? Now, why is that? Because remember that the empirical formula mass, that's going to be the lowest whole number ratio of something. And what we give you as the molar mass is either going to be equal to the empirical formula mass, meaning that they're the same, or it's going to be some whole number value that is a multiplier of that. Okay, so once I have this number, this whole number, now each of that big number, let's say it's a 3, I got to multiply that by my actual empirical formula. So for example, here you have an example. It says a compound has an empirical formula of HO and a molar mass of 34 grams per mole. Remember, I told you we were going to give you this value. We're going to give you the molar mass. Okay, what do you have to do? You have to calculate the empirical formula mass. All right, and so we're giving the empirical formula. Now you have to calculate the mass of that. So you just have to add up the H and the O. And that's what we did. I added up 1 oxygen, which was 16, plus 1 hydrogen, which is 1, right? And so I get 17. Excuse me. So I take my 34, was given to me, right? And divide by the 17, which I calculated, I get a whole number. Remember, I told you this was going to be a whole number, right? And so that whole number now just needs to be multiplied by whatever my empirical formula is. And so I just have to multiply it out. And so I get H2O2. Okay, so that's what molecular formulas are. It's not really too hard. Probably the hardest problem out of all of this stuff was doing the empirical formula. Once you have the empirical formula, then you can figure out molecular formulas really easily. I'm going to have you try it here, okay? So this is going to be a pause and practice. A compound has an empirical formula of NO2 and a molar mass of 92 grams per mole. Calculate the molecular formula. All right, so we're going to pause and practice and see how you do. And we're back. Let's see what we came up with. Okay, so remember the first step was to figure out our empirical formula mass. And we said that we'd give you the molar mass, right? And yeah, we've done it again, just like we said we would, right? And so my nitrogens, what are my nitrogens? Well, nitrogen has a molar mass of 14. We're just going to skip the decimals for right now. Don't skip the decimals when we do it. All right. And then oxygen has a molar mass of 16, but we've got 2 of those, right? So we're at 32 there. 32 plus 14 is giving us a total of 46. Okay, so we've got 46 grams is going to be our empirical formula mass. And we remember we said to take the total molar mass, all right, and divide by the empirical formula mass, and we would get a whole number ratio. Guess what? We get a whole number ratio. It's 2. And so what do we do with that? Well, we take our empirical formula, which is NO2, and we got to multiply 2 by each of those. So our final answer will be N2O4. Okay, we'll box that answer. Is that what you got? If you did, you are a superstar. I know you are amazing. Good job. Okay, so if you didn't get that, then make sure to ask me some questions. Let's talk one-on-one and let's get this stuff figured out because I want to help you to understand this, okay? All right, so I think we've done what we needed to do today. Let's check our objective review. All right, so calculate the percent composition from the formula for a compound. All right, percent composition, that's the percent of each of those. Yeah, we can figure that out because we can take the whole molar mass and then we can figure out how much of those individual molar masses are in that whole molar mass, right? And then determine the empirical and molecular formulas for a compound. We just did that. A little complicated to go through again right now, right? But let's see if we have our criteria as a review here. Given the formula for a compound, I can calculate percent by mass of each element in the formula. Yeah. Give you a formula. Say it's H2O. Can you calculate the percent by mass of each element? Yep. You just got to go to the periodic table, right? Get those molar masses out, divide by the total mass. I can use percent compositions. Okay, it's 16% of this and 17% of that and 18% of that, right? Can I be given that? Can I take that and turn that into an empirical formula? Yeah, I just take those percentages, percent to mass, mass to moles, divide by smallest, multiply to a whole. I got a rhyme I can use to figure out that percent or how to figure out that empirical formula, right? And then can I take that empirical formula and then the molar mass that you will be given and determine its molecular formula? Yeah, just take the molar mass divided by the empirical formula mass. You'll get a whole number, multiply it out through the empirical formula, and you've got your answer. So cool stuff. Got to practice it, right? Practice is going to make perfect. You're going to get better and better at it. So remember to ask me questions if you don't get it. But I think you're on the right start, right? You've started enough. You're on the right track and ready to go. All right. Well, I hope you have a great day. Be kind to one another. God bless you.